lab, we're going to focus on molecular or covalent compounds. Got to give them fair treatment. So we talked about the special electrons. The valence shell is all the electrons that are at the highest N. And so this kind of builds on how we know how to configure electrons. And electrons come and go or are shared so that all atoms get a rare gas configuration. Mostly. There are some exceptions to that. And we have the situation where it's just a single atom that's losing or gaining electrons. Or we have the deal where, and we'll get to actually, today's lab is in parts. So we're going to focus on monoatomic ions, and then there'll be a second part with monatomic ions. And the third part, we're going to talk about polyatomic ions like sulfate, nitrate, phosphate, that sort of thing. Those are ions that have more than one atom stuck together running around. So an ion is something that's not neutral with regard to electrons and protons, right? We talked about how metals tend to form cations and nonmetals tend to form anions. Cations are positively charged because they've lost an electron or 2 or 3, and anions are negatively charged because they've gained an electron 2 or 3 compared to the protons they have in their nuclei. So this is where, if you, maybe on the outside of your periodic table, I don't know, somewhere in your mind, I mentioned this in class where you should think kind of, on the next slide. You think kind of like 1A, group 1A is a +1 charge, group 2A is a +2 charge, group 3A, now these would just be the metals, are a +3 charge, so kind of keep that in mind. And then with regard to the anions, I usually start with the halogens. They're -1, they pick up 1 electron, and you go over that 7A. Go over to 6A, they pick up 2 electrons, -2 charge. These would be the nonmetals. And then the nonmetals in 5A pick up 3 electrons, become -3 charge. So just kind of keep that in mind, how that works. Now this might be a little new, I can't remember how far we got, but when we write a formula of an ionic compound, the net charge needs to be 0. So whatever pluses you get with your cations need to have the same negatives that you bring with your anions. And so that's one of the tasks that we'll be coming up with today, how to write neutral formulas for ionic compounds. So we're going to focus, like I kind of mentioned, today's lab is 3 parts. The first part is just 2 different elements that we go to our closet, we pick a metal, and we pick a nonmetal, and we want to make an ionic compound out of them. Okay? So, for instance, we could go to sodium's a 1A. There's its 1 valence electron. Of course, it's going to lose it, become +1 charge. Fluorine is one of those halogens. It's a 7A, so we get 7 dots here. And so it will become a -1 charge. You get a +1 and -1, and then that's actually how they go ahead and make, there's a chemical formula. There's an ionic bond between this cation and this anion. So it all works pretty well. Sulfur is a 6A nonmetal. And so it'll pick up 2 electrons, and picking up 2 electrons, it forms a -2 charge. But this is a good example of, can you see where we have to have 2 sodium, so it's Na2S, as reflected down here, because, and sometimes I'll do it like this. If we go ahead and do just like a little math to see if the formula that we've come up with is neutral, looks like, woof. Come on. Like this. So like up here, I usually do it on the formula. So we have 2 sodiums, they're both a +1 charge, and we have 1 sulfur, and it's a -2 charge, and that equals 0. So that's kind of the whole neutral thing. The formula for magnesium chloride is this. Magnesium is one of those alkaline metals, a 2A element, so it's going to form a +2 charge. You can hang your hat on it. I kind of mentioned that in lecture the other day. And chlorine is going to form a -1 charge. So if we check its neutrality, we have 1 magnesium, it's a +2, and we have 2 chlorides, and they're -1. So again, you know, that's the correct formula. And so you're gonna, that's a check for the correct formula, and we're gonna talk today how you can make your own formula. And I'm gonna introduce something that I like, is called the crisscross method. So one of the things about it, though, and I think I mentioned this in class, you know, you guys probably tell me, or you would tell me, that the formula for sodium chloride is this. Notice that it's not this. We don't do that. We don't put the charges up there. Usually the cations, the metal, is written first, kind of from left to right. And this will come into play later. When we have actually, for instance, what's an example? Magnesium nitrate, MgNO3 nitrate. Maybe you already knew that, but NO3 is a polyatomic ion. It runs around with a -1 charge. So if I need 2 of those, which I do, I'm going to have to put this, it's kind of like math. I'm going to have to put that quantity in parentheses, and in the lower right-hand corner, I'm going to put a 2 to show I have 2 of those. So that would be the third part. So do you have these? Do you have the slide? You have the answers? Okay, so those can be, these can be helpful sometimes. So you see, oh no, I guess you don't have this one.
I don't have that slide.
Okay, well I just have a few of these, and this is a good one to introduce what I call the crisscross method. So you take the magnitude, not the charge, but like how big the charge is, and you crisscross, and I'll show you what I mean. So, for instance, if I want to write the formula for KCl, you probably say, well, if I had 1 K plus 1 and 1 Cl minus 1, it's neutral, and you're right. So that's kind of anticlimactic. How about this one? This is a good one for the crisscross. So I know aluminum is a 3A metal, so it's going to lose those 3 electrons and form a +3 cation. I know sulfur is 6A, it's going to pick up 2 electrons and form a -2 anion. Crisscross looks like this. Again, it's just the magnitude, so I'm going to take this 3, and 3 is the number of sulfurs or sulfides I need. I'm going to take this 2, and 2 is the number of aluminums I need. So if I rewrite that, this is what I come up with. So it's crisscross. Crisscross applesauce. We can check the neutrality like we've been doing. So I have 2 aluminums. They're each a +3. And I have 3 sulfurs, and they are each a -2. So yeah, I'm in good shape. So the crisscross thing, there are some exceptions, but it'll always work. Sometimes you have to kind of clean it up. So how would this work then? How many FEs do I need?
1.
Very good. And then how many BRs do I need?
3.
You got it. Perfect. How about this one? How many AGs do I need?
2.
Yep. How many O's?
1.
Very good. So you need to be able to, for your next unit exam, to be able for ionic compounds, if I give you metal and I give you the non-metal, you need to go ahead and make a neutral formula unit just like you did. And you'll do that in your exercise today. The other thing is you need to be able to name it. So for naming ionic compounds, you give it a first name and a last name. The first name is the name of the cation, because it's usually written cation and then anion, and the last name is the name of the anion. So the cations, for the first of the 3 parts we're doing today, it's pretty straightforward. It's just the name of the metal, okay, for the first part, as long as it only forms 1 stable ion. And I kind of alluded to this. I said you can hang your hat on the charge that these metals form. And then I said these other ones, not so much, okay? So if it only has 1 stable, one stable form, then you just give it the name. So all of the 1A, 2A, 3A metals, and then we get to, and I'll pull up my periodic table here, and we get to go into the transition elements, the transition metals, the B group metals. We pick up 3, and they're listed there. Okay. So all of these guys, +1, +2, +3, fine. And then here, kind of embedded, we have zinc, cadmium, and silver. They're all clustered together. And like the slide says, silver is a +1, zinc and cadmium is a +2. And the fact that they're always that means that they fall into this category where if they are the metal, then you just simply give the name. All right. So how about the nonmetals? And I think I saw the slide in there. The nonmetals, we basically lop off the end. So if it's just a monatomic nonmetal, we lop off the end of its name and put IDE. And I feel like I'm almost rude, IDE, because there's something called an ITE. We're going to actually go in part 3 to coming up. So enunciation is important. So you have these, and actually these might come in helpful with today's lab. So in naming it, now it doesn't have anything to do with crisscross, we're writing the neutral formula for the compound, but in naming it, this is going to be your last name. All right. So let me kind of pick a couple, and I'll show you how this works. So this is the first of 3 parts. So if you turn the page, do you keep going? Keep going. Right there. Okay. So there's part 1, 2, and 3. So I'll pick on, or you can help me pick on, let's look at D. Okay, and we'll kind of do that together. So D has Na+, but we could actually pick that off the periodic table. We're going to find sodium and sulfur, and those are the ions you're looking at. So what would be the, next to it I want you to write, what would be the neutral formula?
Na2S.
Yep, Na2, and don't forget to make those subscripts. Sometimes they get to be kind of floaters for some reason. Na2S, perfect. And so what would the first name be?
Sodium.
Very good. And what would the last name be?
Sulfide.
Sulfide, very good. Yep, it comes from sulfur. You got it. Sulfide, perfect. So let's skip down to the bottom, and I'll kind of show you how that goes. Let's go to E on the bottom. And so here you're given the name calcium phosphide. And this is called, the next step I want you to do right next to it is called coming up with the component ions. So I want you to tell me calcium, what sort of charge is that?
Calcium is
Yep, so this is where it's just, well, all of these are the same.
Yeah.
Yep. So what charge is it?
+2.
+2. Very good. And then how about phosphide? Put P here. And then you can see it on the periodic table. You got it, yep. And so as much as possible, I would just start to, for that particular thing, get used to finding on the periodic table and drawing your conclusions. Yep, -3. Perfect. And then, so on the test, on your unit exam, you'll be given a name, and I won't ask you to write the component ions like that, but I do, because that helps me have a fighting chance of writing a neutral formula. Okay, so what's the neutral formula?
CA3.
Yep, how many CAs do we need?
We need 3.
Very good. And then how many phosphoruses do we need? 2. Okay, cool. Well, I'll give you a little bit of time and kind of see what you can do with those, and then go on to the next part. It's got a mind of its own. So the second part only does one thing, and that is to kind of swap out the metals, because it introduces metals that form two or more possibilities with regard to their ions. You probably have in your, yeah, you have something that looks kind of like this somewhere, maybe smaller versions. Yeah, right here. Yeah. It's really hard to see, but that is that. Oh, you got it. Good. That's bigger. So we can't just call it, for instance, copper, because we have two forms of copper. We have to designate that in the name. So we have two options, and they look like, do you have a sheet that looks like this? Wait, no, this one. Yep, thank you. Yep, very good. So we're going to go with this one, but some people who have already been exposed to how to name compounds with ion compounds are already have these in their mind. But so, for instance, I would call this one. We call this one iron 2, plus 2 cation. Some people would call it ferrous. So, okay, I just think it's easier. And notice that the Roman numeral is the charge. Okay, cool, very good. So what I tell people, and this is the way it's done, that if you find, let's see where you, so yeah, here's the problem, is people want to use Roman numerals for all of the metals, but notice this says, when do you not use Roman numerals? So you don't use Roman numerals in the name if it's this, 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 or like you have it circled, if it's zinc, cadmium, or silver, no Roman numerals. And then when you use Roman numerals, everything else, all the other metals. And the Roman numeral in its name is the charge, okay? So, do you have this one? Okay, so can you find calcium on the periodic table? So would you call it calcium or calcium 2? Nope, because calcium is, yep, just plain old calcium. Yep, very good. How about potassium? Potassium. How about barium? Just barium? You're right. Sorry. How about lead? Lead plus 2.
Lead 2.
Very good. Got it. How about, and then that would be lead 4. How about sodium?
Sodium.
Sodium. Very good. Aluminum. Perfect. Cadmium.
Cadmium.
Very good. That one throws me off, but you're right. Magnesium.
Magnesium.
Yep. And this one should not be on here. It's actually ammonia. So it's one of the polyatomic ions. Okay. It's like ammonium, sorry. Okay, final answer. All right. How about these? So would you go iron or iron 2?
Iron 2.
Perfect. The next one?
Iron 3.
Yep. How about zinc?
Zinc.
Perfect.
Copper 2.
Perfect.
Copper.
Copper 1. Yep.
That one. Nitrate 2.
Nickel 2.
Oh, nickel.
Nickel 2. Uh-huh.
Nickel 3.
Nickel 3.
And then be silver.
Just plain old silver.
Yep, and that would be.
It's 80, so it's atomic number 80. So you find it on the periodic table, and if it's, so the fact
Yeah, I
that
know,
it's
I just forgot.
oh, mercury, sorry.
Mercury.
Mercury 2, yeah, you got it. Very good. Okay, so let's do a couple of the next part. So it looks like this. Let's pick on, D is a good one. D will kind of tell us what I think. So you're given the component ions, Cu 2 plus and O 2 minus.
It's just C plus.
What's that?
It's just C.
Oh,
plus,
no, I'm on D. So C is, oh, Yep, I'm mixing it though. Okay, final answer. How about that? Does that look
Yes.
like D? Okay, thank you. That does look like D. All right. So write the neutral formula next to it. And tell me what you write.
Cu2S2.
Now this is I did this one on purpose. Actually, that's not quite right. If you can take the number that you have and divide through by a number and get another set of whole
So we
numbers.
want Cu in parentheses, or Cus in parentheses too.
Nope.
No?
I just wanted you to go divide the 2 and the 2 by 2 and get 1 and 1. So CUS.
Okay.
Yeah. So that's one catch with crisscrossing, but cool. And then, so what would the first name be?
Okay, copper 2.
Perfect. Copper 2, and then the last name?
And will be sulfur.
It comes from sulfur, so it's did you say sulfur? Yeah, it's
Oh yeah, sulfide.
sulfide. Yep, you got it. You got it. Perfect. Okay, now let's look at the bottom. Let's do, how about G down at the bottom? So the name we have is cobalt 2. And then the first stop is we're going to write the component ions. Cobalt 2 fluoride. So what would the component ions be? So cobalt is CO, the element CO. And then what charge would that be?
2 is that?
Yep, plus 2.
2 plus.
Yep, you got it. And then what would fluoride be?
Fluoride will be F minus.
Yep, very good. And then with the component ions, we can go ahead and write the neutral formula. So what would it be?
COF2.
You got it, COF2. Perfect. Well, I'll give you a little bit and take a look at those. Good job. Compounds, but we're going to introduce ions that have more than one atom stuck together. So you can't break up, for instance, this ammonium, NH4 plus, those 5 atoms are stuck together, all running around with a +1 charge. But like when we go to put ammonium with an anion, we go ahead and crisscross like normal. And if we need more than one NH4, we have to put it in parentheses and put outside how many we need. So you should have something that looks like this in your flow sheets probably. And so what I tell students is if you would, go ahead down here, write those 2. So yeah, ammonium NH4 plus. And that second one's one of my least favorite. So it's mercury 1. G2 runs around with a +2 charge, and that one is the most tricky. So the thing with this guy right here is he has a mercury atom and a mercury atom, so they're totally stuck together, but they are all running around collectively with a +2 charge. And so I think the reason we call it mercury 1 is you kind of think of that +2 is distributed among 2 mercury atoms, kind of +1. So, and the reason they aren't on that is because this one is, the title of this is anion, so these are all negatively charged, or these are positively charged, so I can see why. A lot of those that we see, the polyatomic ions, are actually have oxygen in them, but these are exceptions. And so, for instance, on that table you've got, if you want to know where CN is, you can either look at carbon or nitrogen. It looks like CN is under carbon. Okay. So these are exceptions. They don't have oxygen with them. And then this is where I tell students in this class you don't have to memorize a lot. You do not. But you do have to memorize these guys. And I've got flashcards I'm going to give you for extra credit. what will replace a homework. You can do these flashcards, at least cut them up. Okay, so, all right. So the ones that have oxygen, that's where we run into problems. And I mentioned the IDE, like I overly enunciate, like phosphide. The reason I do that is because there's something called phosphite. Phosphide, IDE, is one atom. Phosphite has oxygen there. Okay, so ite or ate. So these are exceptions. They don't end in ite or ate, but you need to memorize hydroxide, OH minus, cyanide, CN minus 1, triide, minus 1, I3 minus 1. So what do we do with the whole oxygens things? Well, one sort of kind of thing to put in the back of your mind is if it has more oxygen, it's gonna end in ate. And I think like I ate too much oxygen. And that reminds me, relatively speaking, to that particular element, it's going to have more oxygens. And then the ite ending is going to have less oxygen. But it differs by element. So for instance, if you find sulfur on here, you can see that we have a sulfite and a sulfate. And you're going to have to know sulfite is SO3 2 minus, sulfate is SO4 2 minus. But then if we look at nitrogen, nitrogen has two options too. But they differ. You can see what I'm saying. It doesn't have 3 and 4 oxygens, it has 2 and 3, and it goes with the pattern. One with the fewer oxygens, nitrite, one with the greater oxygens, nitrate. But one thing it has going for it is both oxyanions have the same charge. So for instance, the sulfite and sulfate both -2, nitrate and nitrite both -1. So yeah, just gotta memorize it. And then we get to the halogens. So you can kind of see already, we've got some options with regard to chlorine, bonding with oxygen, bromine, and iodine. So smack dab in the middle, by the way, they're all -1. Smack dab in the middle, ClO2, -1, ClO3, -1, chlorite, chlorate. And then if you're hypothermic, it means you're low with regard to your thermal energy, hypo. So if we take off one more oxygen, it's going to be ClO -1, and it's going to be hypochlorite. And I don't know what to say about the per. We add the prefix per if you have more oxygens than the chlorate. So perchlorate is ClO4 -1. And you can actually see that chlorine does that, bromine does that, and iodine does that. Okay, that same pattern. There's another hint. For some cases, we kick in a hydrogen, and as you kick in a hydrogen, notice that actually this is the polyatomic ion, it's going to tap the charge down 1 less negative. Kick in 2 hydrogens, it caps it down 2 less negatives. 3, it'll take it out 3 less negatives. So an example of that, if you look under sulfur, you have the sulfite, SO3 2 minus, and then you have the hydrogen sulfite. And now hydrogen sulfite is HSO3. Instead of being 2 minus, it's 1 minus. So those are just hints. Sulfate, hydrogen sulfate, similar pattern, -2 to -1. Carbonate to hydrogen carbonate, and these I think of it as hydrogen carbonate, but you might have learned as bicarbonate. This would be bisulfate and bisulfite, so that would work too. And then phosphorus, phosphate is PO4 3 minus, and you may know some of this with your water studies. And so hydrogen phosphate is HPO4. Now it's 2 minus instead of 3 minus. This actually is there's another one. There's only 2 places I think that you need to memorize that we use the word di. We never use tri. Okay, well, yeah, tri in naming ionic compounds. But this is dihydrogen phosphate, so it's H2PO4 instead of being, now since we kicked in 2 hydrogens, it taps down the original -3, 2, so it makes it a -1 instead of -3. All right, so let's take a look, do a couple together in that last part. So for instance, with the component ions, what would you do with, try to find one. Okay, let's do F together. So F, the component ions, is nickel +2 and HSO4 minus. Okay, so what would be the neutral formula for that?
It'd be,
Ni, yep.
HSO2.
So we need two of these, right? So what we're going to do is kind of in math, like we do in math, where I'm going to do HSO4, and I'm going to put a 2 outside. Yep. Very good. And so what would the first name of that be?
Nickel.
Would we use Roman numerals?
Nickel. Yeah.
Okay, nickel 2. And then what would the last name be? You probably have to look this up.
Hydrogen phosphate.
Not phosphate, hydrogen.
Sulfate.
Yep, hydrogen sulfate. Okay, so let's do one on the last page. Let's pick on I. Okay, so for I, we're given the name lead 4 and nitrite. So we need to write the component ions first. So what's the lead 4 look like?
That is a PB.
Uh-huh.
So the PB3.
Oh, sorry, you can't read this. This is supposed to be an IB. So actually, so I don't know if sometimes students don't know Roman numerals, or do you know Roman numerals? Okay, yep. So, yep, IV, that's 4.
Yeah.
Yep. So it'd be PB plus 4, and then what about the nitrite?
Nitrite.
Mm-hmm.
Nitrite, that would be NO2 minus 1.
Perfect. Okay, so what's the neutral formula then?
Neutral formula would be PB. And then in parentheses NO2, and parentheses, and then subscript 4.
I'm liking it. Cool. All right. See what you can do with that last part.
Okay.